How to find the beautiful structures of nature. What kind of relationship does math have with nature? When we think of nature, we usually think of trees, grass, and animals deep inside the mountains or things that have always been in existence. When we think of math, we usually think of combinations of numbers and letters needed to make formulas and solve problems. Because of such stereotypes, it is easy to think that nature and math are not related at all. However, it is worth noting what Ian Stewart, a British mathematician and popular science writer, once said. According to him, people usually think of math as just setting up an equation and solving the problem. Stewart claims that if math is an iceberg, solving problems is just a tip of the iceberg. He also expresses his disappointment in people judging too quickly that solving problems is all there is to math. Then what is math? There is a close relationship between math and nature. Math is the study of discovering the secrets of nature. By finding the secrets of nature, we can discover things that can make people happy. Therefore, it is wrong to say that being good at solving problems means being good at math. Points, lines, planes, and dimensions are basic elements in geometry. All objects in nature has a location, shape, size, color, weight, and so on. However, in geometry, where we deal with figures, we are not focused on what constitutes an object or its weight or color. We only focus on its location, shape, and size. Only when we can consider such things can an object be called a figure. Figures on planes are called plane figures, while figures on space are called space figures. Space figures that have a location and shape, length, width, and depth are called three-dimensional figures. In basic geometry, a plane, face, is a flat surface that forms the boundary where two dimensions meet. It has an area, figure, or location, but no thickness. A line defines the boundary of a face. It also has a location, shape, and length, but has no depth or size. A point is a shape that marks the end of a line and it has no size. Geometry does not provide an exact definition of these basic elements of points, straight lines, and planes. They merely have axioms that regulate the relations between them. Examples of these axioms include: there is only one straight line that goes through 2 points, a straight line can be drawn between 2 points, 2 straight lines intersect at 1 point, a straight line connecting 2 points above a plane is above the plane, and etc. Within these axioms, we define a point, a straight line, and a plane. That being said, what are axioms? Axioms are the most fundamental propositions that are accepted without proof used to construct a logical structure. For example, Euclid's geometry has a few basic axioms, including axioms on parallel lines. Axiom is about choosing a rule that describes a structure's property to be able to define it. In Euclid's geometry, axioms are propositions that don't need proof or can't be proven but is intuitively known as an obvious truth and at the same time is a premise for other propositions. However, today, without relation to its truth value, A proposition can be considered as an axiom if it is used as a premise for a deductive logic and does not require proof. In logic, philosophy, math, and computer science, propositions are declarative sentences that is either true or false. Mathematical propositions are referred to as theorems. Apart from theorems, propositions are hard to define. In classical logic, assigning a correct proposition as true and a wrong proposition as false is known as a truth value. Around 300 BC Elements, the textbook of geometry, was published at Alexandria. It is believed that Euclid was the one who did this massive undertaking. Elements is the most translated and published book in the West after the Bible. Since its first edition in 1482, over 1,000 editions have been published by the 20th century, making it the second most sold book in the history of humanity, just after the Bible. Elements, in its 13 books and 465 propositions, discuss plane and solid geometry, elementary number theory, and more. In Elements, Euclid presents basic assumptions, definitions and mathematical rules, also known as axioms. From construction of simple triangles to Platonic solids, the book includes fundamental elements to prove from simple to complicated propositions. The beginning of the first book of Elements lists 5 propositions on geometric properties, known as postulates. The first 3 postulates are about constructing geometric figures. These fundamental mathematical assumptions are necessary to have basic knowledge in geometry. For example, the first postulate shows that a strategic line can be drawn joining any 2 points, and the fourth postulate states that all right angles are congruent. But these 2 postulates actually connote a more profound meaning. This proves that when geometric construction is not relevant to location. In other words, no matter the location, we can apply the same rule anywhere there is space. The fifth postulate, known as the parallel postulate, is the most widely used postulate. It states that given a straight line and a point not on this line, you can only draw one straight line through this point that will not meet the other straight line. This shows that no matter what, 2 parallel lines do not meet each other. This postulate also defines the nature of space. Such postulates also played a critical role in establishing the framework of Euclidean geometry. Non-Euclidean geometry is a type of geometry that does not accept the parallel postulate. For example, the longitudes on the map are parallel on the equator but meet at both poles. From Book 1 to 6, Euclid defines the basic terminology and deals with plane geometry. More specifically, Book 1 and 2 talks about triangles, parallelism and basic properties of rectangles. Circles are discussed in Book 3 and 4, and ratio and Eudoxus' work on irrational numbers are in Books 5 and 6. Books 7 through 10 talks about the number theory. Books 11 through 13 discuss three-dimensional geometry, uses of Euclid's method of exhaustion, and proves that only 5 Platonic solids exist. There are mountains, rivers, oceans, rocks, animals, and plants in the nature we are living in. We can find beautiful points, lines, and planes within the components making up nature. We can also find mathematics, a tool made to discover the secrets of nature, and its expressions, such as points, lines, and planes within nature. Everything that exists in nature has a name. The first thing scholars do when they discover something new is to name it. They do not just make up any random name but ponders for a long time to assign a name that helps indicate its looks and characteristics. It is the name of an object that helps us to immediately visualize in our head. Have you ever imagined a world without points, lines, and planes? Without them, nothing would be visible or tangible. It would be a desolate world where we cannot see or draw anything, even if we desperately want to. If there were no points, lines, and planes, the world would be an empty space with nothing visible. However, we should be cautious not to make the same mistake Pythagoras made and consider the world and everything within it as polygons. For a moment, imagine that the world is only defined as polygons, and the sides of these polygons are ratio of integers. Pythagoras held constant ratio as sacred. It was only with the discovery of a side that can't be stated as a constant ratio on the pentagram, a symbol of the Pythagorean school, known as irrational numbers, a number that cannot be written as a ratio of two integers, that allowed scholars to finally understand more in depth about numbers, the key to unfold the secrets of nature. However, many mathematicians had to work arduously to find the secrets of nature that cannot be explained with Pythagoras' rational numbers, numbers that can be expressed as a ratio. Of course, if nature could be expressed as a polygon, nature would have given us stability and peace. Anyhow, the purpose of studying points, lines, and planes within nature is to understand the beauty of structures in nature. Moreover, it is to reveal the secrets of nature more quickly by discovering the designs and patterns by observing nature. A shape is not a word limited to mathematics. In fact, it is a natural language expressed as a picture designed to help us better understand the patterns discovered through the observation of nature. How are points, lines, and planes made, and what message do they give? Surveying techniques in ancient Egypt was part of the lifestyle and the foundations that helped the country to develop. For these reasons, ancient Egyptians researched extensively on shapes. Egyptian mathematics consisted of solving daily life problems, and it passed down from Alexandria to ancient Greece. However, there is still one main difference between Egyptian mathematics and Greek mathematics. Egyptians used math as a tool to solve problems in their daily lives, while Greeks considered shapes as objects to study. Thales, a mathematician who accurately measured the height of the pyramid just using a stick, was able to express logical reasoning, such as proportionality, that contributed in the advancement of geometry. Thales' way of doing math, proving even seemingly obvious math content, became a tradition in Greek mathematics. Showing how you got an answer and specifically showing the process of solving the math problem is a characteristic of Greek mathematics. As mentioned earlier, an ancient Greek mathematician, Euclid made a significant impact on building Greek geometry system through his book, Elements. Euclid's mathematical approach is still considered a great example today to those studying geometry, even 2,000 years later. Euclid did not write everything Elements by himself. Although he himself did proved and proposed a few, he mostly referenced well-known mathematical knowledge at the time. Natural philosophers, represented by Thales, used the natural law they learned through years of experiencing nature and recorded their measurements in a language the majority could understand. Elements is a compilation of such measurements made by natural philosophers. Today, Euclid's mathematical approach is often used as the base for modern mathematics. Newton's Philosophiae Naturalis Principia Mathematica, also referred to as Principia, and Spinoza's Ethics both apply Euclid's methods follows Euclid's methods. Principia, written in Latin by Newton, who completed modern mechanics, is comprised of 3 books. After the preface, it deals with the foundations of mechanics, the quantity of matter, mass, quantity of motion, momentum, and force. Then, after explaining absolute space and time, the 3 most important laws in modern mechanics is explained. The 3 laws are also called the law of inertia, the law of acceleration, force is equal to mass times acceleration, and the law of action-reaction. Principia is of great significance in that it compiled research done on force and motion since the ancient times and laid the mathematical foundations used in mechanics. The 3rd book of Principia states clear solutions to the many problems Copernicus' heliocentric theory, especially by proving Kepler's discovery of planets' elliptical orbits. The last sentence in Ethics, but all things excellent are as difficult as they are rare, accurately delivers Spinoza's ideology in life. After being ostracized and shunned for a long time, Spinoza's theory was finally accepted 300 years after his death as a key theory to understand reality. Spinoza, an outsider, was able to draw out an original insight from the invisible crack that those with riches and power couldn't see. He continuously sought out for truth during his years of profound solitude. Although during his time Spinoza's philosophy had nearly no influence on the society, its power grew as time went by and touched many people's heart. Today we can now understand the infinite power of truth. When studying math, it is important to know the exact reason for studying that chapter. In addition, it is important to know the logical basis behind the mathematical theories studied in the chapter. The topics dealt with in this chapter, points, lines, and planes, are essential elements of figures. It would be great if we could know how points, lines, planes are made and how they relate to each other. When 2 planes meet and share a line, we call the line a line of intersection of the 2 planes. A point is determined by the next 3 conditions. A vertex is a point where 3 edges interact. 1. A point is determined when 3 planes that are not parallel to the line of intersection of the 2 planes. Find straight lines going through planes in our daily life. 2. When a straight line meets a plane we get a point. 3. When two straight lines meet, we get a point. There are two conditions in which a line is created. 1. The two planes that meet each other create a straight line. 2. The two dots create a straight line that passes through the dots. There are four conditions in which a plane is created. 1. Three dots that are not on the same line create a plane. 2. A straight line and a dot that is not on the line create a plane. 3. Two straight lines that meet each other create a plane. 4. Two straight lines that are parallel to each other create a plane. Points and lines are the basic elements to create artworks. The dots in mathematics are the most basic unit of shapes, which have no direction and area, but only location. However, points in arts, referred to as dots, can come in many sizes. Through numbers, locations, brightness, and sizes, materials used to draw, and relation with others, dots can express their shapes and movements. Through these, dots can convey spatial and unique feelings. If a distance between dots is small, it feels like it moves fast. On the other hand, if the distance is large, it feels like it moved slow. By changing a size of dots large or small, it can incite a sense of movement or space. New shapes can be also created by overlapping the dots. Because a line has more than one dots connected, it can show a position and direction, but no area or volume. It is the fundamental element to describe specific shapes, so it is essential in order to create artwork such as drawing, animation, and painting. In addition to creating a form of objects, lines are also used to express contrast, strength, textures, spaces, and movements. By carefully considering the lengths, thicknesses, directions, brightness, materials used, and distances between lines, you can specify the feelings you want to convey. Depending on how dots are connected, a straight and curved line are formed. Straight lines usually incite a sense of speed, agility, and simplicity. On the contrary, curved lines gives a feeling of flexibility, affluence, and elegance. Thin lines convey delicate and sensitive feelings, while thick lines may feel bold and dull. Depending on a degree that are tilted, horizontal lines incite flatness and balance, vertical lines are related firmness and elevation, and diagonal lines show a dynamic feeling. If we can figure out the language of nature, where can we use it? If you want to deal with a subject in mathematics, things can be easier by drawing it in a picture. As mentioned earlier, mathematics is a study of discovering the secrets of nature. The ideal way of studying mathematics starts from finding unique shapes through observing nature. However, a pattern, a group of unique shapes, is not easily exposed. Thus, we can get closer to the secrets of nature when we can draw the unique shapes and put numbers and letters to each of them. Drawing what you are interested in means that now it becomes a subject you can deal with in mathematics. Shapes such as points, lines, and planes are the language that mathematics uses, and also they are the language of nature. Shapes are the idea found in unique patterns achieved through observing nature. Pointillism is a way of painting that uses dots to draw. It is a painting techniques invented to express colors like the rainbow, showing various colors caused by dispersion of sunlight. Pointillism only uses dots to draw. Painters dip a tip of brushes into paints and draw pictures with small dots. Usually when applying colors, primary colors are mixed in a palette and painted with brushes. However, for pointillism, each brush uses only one primary color. Different colors of dots are drawn over one another to express various colors. Upon a closer look, what you see in pictures are different colors of dots. However, in a far distance, separate dots disappear and blend into one big shape. For example, when you mix blue and yellow, it becomes green. In pointillism, each brush uses blue and yellow color respectively to paint each color of dots. When blue and yellow dots are overlapped, the color we see is green. Similarly, it is very interesting to find mathematics and arts. The door to the world of mathematics and the door to find out the secrets of the nature are the same. If you look closely at a transmission tower, you will find a lot of triangular structures made of iron. Although it is made with thin steel frames that are connected, it does not easily collapse. It is because a transmission tower is built based on mathematics that finds out the secrets of nature. Just like thorns of roses, with triangles that have a property of not changing easily the shapes, you can make a strong structure. Cranes that are used to build tall buildings look weak, but they are actually very strong. It is because they are made with many triangles connected to each other. Like this example, although corrugated cardboards are made of fragile paper, they are light and strong because of the triangles in it. You can see easily a hemispheric roof, which is known as dome, in science museums or big assembly halls. It was Buckminster Fuller, 1895–1983, an American architect and inventor, who designed the structure known as geodesic dome. Fuller claimed that humans, who have chosen specialization to preserve civilization, involuntarily encountered a new antibody called computers. In addition, he said professionals will be completely replaced by computers. He has a point when thinking about the recent fourth industrial revolution like artificial intelligence. Before he invented geodesic dome, he focused on studying to build dimension structures, such as houses, cars, and restrooms, that can be easily assembled and mass-produced. Architecture industry remembers him as a person who paid attention to the concept of sustainability and regeneration from very early on. Norman Foster, 1935, a master of high-tech architecture who followed Fuller as a mentor, acknowledged Fuller as the essence of a moral conscience in his interview with New York Observer in 2015. He also said Fuller always warned that Earth is vulnerable and also emphasized that people should take the lead to protecting the planet. A word geodesic means shortcuts, but in architecture, it represents a geometric design technique that triangles are connected to each other. With the word dome, which represents a hemispheric roof, added at the end, geodesic dome is a construction method to build a hemispheric structure that is consisted of triangles connected together. Geodesic dome structures have two main advantages. First, they can withstand very heavy weight because faces and edges of triangles are firmly interlocked to each other. Second, the structures are highly effective in utilizing the space since they do not need pillars. It is because the structures hold the triangles very tightly. A geodesic dome is a construction technique to build a strong and spacious structure with minimizing the material costs. The only disadvantage is that this hemispheric structure is not suitable for living in terms of space efficiency. A square made up of 4 straight lines is the most common shape around us. Buildings, rooms, and papers are all squares. However, squares have a property of changing the shape easily. If we use this property, we can make a garment rack or fence whose length can be adjustable to shorten and lengthen. A hexagon has a greater surface area compared to a triangle and square with the same circumference. In addition, hexagons do not create empty spaces like circles, which is known as the perfect shape. This makes hexagons very space efficient. Therefore, houses are often built in hexagonal shapes because the shape of hexagons is close to a circle and it does not waste any space. Moreover, less materials are needed to fill the same space with hexagons. It means the hexagon-based structure will be lighter. For example, the wings of airplane is in the shape of hexagonal honeycombs. Thus, the wings are light and very strong at the same time. A dragonfly's wings have a lot of wrinkles yet are thin and light. However, they do not easily get bent. Because of these properties, scientists are studying its wings to invent micro-flying objects. Have you heard of Sudoku? It is a mathematics puzzle that places all of the numbers from 1 to 9 in a 9 by 9 grid that is consisted of 81 squares. Each number has to appear exactly once in every row and column. Sudoku has an additional rule. It is to place all of the numbers from 1 to 9 in 3 by 3 subgrids as well. It is to fill the empty squares in 3 by 3 subgrids with numbers from 1 to 9 only once. On the contrary, magic square is a mathematics puzzle to fill the numbers from 1 to n square in squares within a n by n grid. The sum of the numbers in each rows, columns, and diagonals should be the same. In other words, Sudoku and magic square are the same since numbers can be used only once. However, the difference is that magic square takes account of the sum of arranged numbers. What is the reason the arrangement of numbers whose horizontal, vertical, and diagonal sums are the same called magic square? Magic square refers to the arrangements of numbers in squares just like a magic. Its history can be traced back to the Emperor Yuan Xia dynasty. A turtle's back engraved with strange pictures was found in the Yellow River while restoring its waterway damaged from annual flood. The numbers from 1 to 9 engraved in the back of the turtle were surprisingly added up to 15 in any direction. Since then, the Chinese believed that it contained the secrets and the truth of the world. They recognized it as an array of numbers that connoted the principles of the universe and foundations for Book of Change, I Ching. Various arrangements of numbers in triangles, hexagons, and circles show the similar characteristics of magic squares, although they are different in shapes. Among them, an arrangement of numbers called hexagonal tortoise problem made Choi Seok-young, a Korean politician in Joseon dynasty, famous. The way of playing it was similar to numbers games containing mathematics and traditional East Asian philosophy. However, it was named hexagonal tortoise problem because it looked like the shape of a turtle's back as a whole. The sum of every number written on the vertices of hexagons, which looks like a turtle's back, have the same total. Shelters are very important to every living organism, including humans. Therefore, all of the living organisms build their own shelters in different and unique ways. Among them, the structures of honeycombs with a unique shape of a hexagonal prism are widely used in everyday life, from buildings to laptops. Why is the structure of honeycombs widely used? The hexagonal structures in honeycombs are the most economical structure that can maximize spaces using minimal materials. It is also a stable structure that maintains the balance and evenly distributes forces. When putting hexagonal structures together, their sides meet each other so no gaps are created. Triangles and squares also do not have gaps between sides. However, in the case of triangles, it needs more materials to build a wall, and a space created is relatively small. In the case of squares, they cannot distribute the forces exerted from the outside. Their shapes are easily deformed because it is vulnerable to be twisted and crushed. However, the structure of hexagons that are empty inside easily distributes the external forces. Therefore, they are strong and highly stable. Let's think about this mathematically. With the same circumference, a circle has the biggest surface area. It is true that the surface area of a single circle is the biggest when comparing with a triangle or square that has the same circumference. However, when attaching multiple circles together, empty spaces are created that cannot be used. Thus, you cannot use the space effectively. However, hexagonal honeycombs are highly effective in utilizing a space by allowing bees to store as much as 30 times the honey of their weights.